That's actually the first known occurrence of that expression. Okay, so this plot gets into this rate at which these large events actually occur. I actually showed this earlier in the semester, but the point of this plot here is that we have a scale on the horizontal axis and a scale on the vertical axis. The scale on the horizontal axis is sort of the nastiness of the event, the equivalent tons of TNT in the explosion that occurs. Starting with relatively small events, hundredths of a megaton, actually, it's a pretty large event, up to 100 megatons of energy. And then we see the time scale on the vertical axis. How often do events of that energy scale happen? Now, you see the curve drops as we go to the right. It descends as we go to larger amounts of energy, right? If that curve went the opposite way, from the lower left to the upper right, we wouldn't be having this conversation right now. Because if that were the case, if the curve went from lower left to upper right, that would mean that there's lots and lots of huge events, and then, we probably wouldn't have had the evolution of intelligent life on Earth under those circumstances. The larger Tunguska events, and events larger than that, occur less than once every 1,000 years, or even once every million years. But the 20 kiloton events occur roughly annually. That's kind of like this explosion of the Pacific Ocean I was talking about. So this is basically something that represents the current state of material flying around the solar system. This curve would have looked very different early in the solar system, billions of years ago, like say about 4 billion years ago. This curve would have looked completely different because that's when we saw the formation of the huge craters on the moon, for instance. Huge craters were formed pretty regularly, 3.5 to 4 billion years ago. So this curve would have looked different, but this is the way it looks today. Alrighty, so let's see. I think we've pretty much covered a lot of this. So this is just talking about some of the relatively close approach asteroids that have occurred. The record, as far as I know, is still this 2008 event when an asteroid exploded in Earth's orbit, only a matter of 2,000 kilometers out. So we do see some incidents of asteroids passing so close that they're actually between the Earth and the Moon. They pass through the Earth-Moon orbit. Because if we're looking at kilometers, the Moon's orbit is around 350,000 kilometers. So the second one on the list actually was only about half the lunar distance out from the Earth. A lot of these objects are only discovered in the year when they actually make their closest approach. Okay, so like for example, if you look at the year 2008, well that object's called 2008 TC3. The 2008 in the name means that it was only just discovered in 2008. Actually, it was only discovered within a matter of days around the time that it passed Earth. And some of these are difficult to detect because they actually come from the opposite direction of Earth's orbit. So the bottom line here is there is certainly the possibility we would have little to no warning about a large impact. So what we're trying to do is actually do a better survey of what's actually out there in space that could come close to us. So that's actually the 2008 incident right there that actually crossed only within 21% of the Earth-Moon distance. All right, just a little bit more. We think we know about 99% of the larger asteroids at this time, but when we go below 100 kilometers, we only know about 50% of them. And 100 kilometers is still a darn large asteroid, still larger than the asteroid that actually caused the extinction. Dinosaurs. All right, so let's get into something that is a phenomenon that's called the Kirkwood gaps, which represents gaps in the asteroid belt itself that are very similar to the gaps that we've been talking about in Saturn's ring system. Okay, so just to review, remember that the gaps that we see in Saturn's ring system are due to interactions with moons orbiting Saturn. Remember that if you get an integer relationship between the orbital period of a particle orbiting Saturn, you get an integer relationship between that orbital period and the orbital period of a moon farther out. What that means is they periodically line up with each other, and then that moon gives a little tug and clears out a gap. Same thing happens when we're talking about the Kirkwood gaps in the asteroid belt. Okay? We see gaps due to exactly this resonance phenomenon that's actually depicted here. The 2-to-1 gap is the strongest. That might ring a bell because that's actually the way we form the Cassini division in Saturn's rings. Remember, the Cassini division is the big, thick, dark black gap in Saturn's rings, which is actually caused by a 2-to-1 resonance with Mimas, one of Saturn's most inner moons. Okay, so when we look at the Kirkwood gaps, the deepest gap is due to a 2-to-1 interaction with Jupiter. That means for every 2 orbits of an asteroid, we get a lining up phenomenon, which means that we get this periodic tug, which tends to clear out the gap, just like what we saw when we looked at the rings of Saturn. Okay, so this is a plot of the number of asteroids in the asteroid belt as a function of their semi-major axis. And what we find is that, remember that the semi-major axis is connected with the period, right? We have p squared equals a cubed from Kepler's third law. So if we're talking about relating the period to be half of the period of Jupiter's orbit, okay, that means we're talking about objects that are orbiting the sun that have a period equal to half of Jupiter's orbital period. Well, because of Kepler's third law, that orbital period of half Jupiter's orbital period implies a definite semi-major axis. And that semi-major axis is right here, around 3.2 astronomical units. So the Kirkwood gap is right around 3.2 or maybe 3.3 astronomical units, because asteroids orbiting with that semi-major axis will get this periodic tug from Jupiter every other orbit, and that tends to clear out the gap, just like the gaps in the rings of Saturn. And there are other gaps that represent all kinds of crazy ratios between the orbital period of the asteroid and the orbital period of Jupiter, like that 7-2 gap over there. It's not a very strong one because you're talking about 7 orbits of the asteroid for every 2 orbits of Jupiter, and that's not reinforced very often. That's a force that's only reinforced every 7 orbits. So it's not strongly reinforced. The most strongly reinforced orbit is the 2-to-1 condition right there, so that's why that gap is the deepest one. And let's see, this is Eros, again, the asteroid of love, we call it. And this happens to be one which not only have we approached it, but we've actually even landed on this asteroid. Okay? It's not a controlled landing, but we'll talk a little bit more about this mission. But basically what you're seeing in that little panel is a GIF image which was generated by cameras on the NEAR spacecraft as it approached the surface of Eros and actually crash landed. It wasn't even designed to land. There's no landing gear on it. But the mission was out of the propellant that's used to actually propel it around in space. So it basically was not controllable anymore. So they used the last little bit of propellant to drop it right down so that you could see these kinds of close-ups right up until it actually struck the surface. And you can see a very boulder-strewn surface with lots of small features there. Okay, so this is Eros again. We've seen that, I showed you the moon of Saturn, Hyperion, a couple of lectures ago, the largest known piece of gefilte fish, you might remember. It's actually orbiting satellite. Here we have not a piece of gefilte fish, but something more like a potato, just a conventional potato. Maybe slightly more relevant with Thanksgiving coming up than a piece of gefilte fish would be, I think. All right, so this object, Eros, was actually explored by the NEAR spacecraft. And what we see is this very strange way that the object was approached, this spiral path that the spacecraft took. And the reason it took a path like this, instead of just coming in and just kind of landing on the surface, is actually for 2 reasons. One, Eros itself is actually spinning pretty quickly, so you can't just come down and land on it because it'll be spinning underneath you and you'll just get smashed into by this spinning asteroid. And the other thing is that Eros' gravity is so weak that it doesn't really guide you down to land on itself. There's virtually no gravitational traction around a very small asteroid like this. So you actually have to fire rockets to get down to the surface. It's the opposite of what you normally think. You normally think you've got to fire retro rockets to make a landing on an object like this. But in this case, gravity is so weak, there's virtually no gravity, and you actually have to fire rockets to go down towards Eros. And that's, again, why it's difficult to do any kind of a controlled landing. So here we see, again, a very strange situation. Very weirdly shaped object, which probably is the result of multiple large impacts over billions of years. And if we take closer looks, we see really odd features, like, for example, here, see that little white blip right there? That's actually a boulder sitting on Eros, but it's not sitting at the bottom of that crater. You know, normally, if you're going to have a boulder sitting in a crater, it's going to roll down to the bottom of the crater, right? Well, it's trying to do that here, but because of the weird shape of Eros, it's actually rolling to the point where it's being pulled toward the center of gravity of Eros. But Eros is so weirdly shaped, it's not a sphere. So that point where it's being drawn to is not actually at the bottom of the crater, it's on the crater wall. So here we see other examples of that. It's just a very strange situation where you have boulders that are stuck to kind of odd places on crater walls, because that's where the gravitational force actually attracts them to. Oh, interesting. Right about this. Okay. Probably most of you recognize the Commonwealth of Massachusetts, right? State? Okay. You have to go with me on this one.